Okay, so now we're going to look at some words that are used in mathematics that we want to make sure that we understand the sort of the math meaning of them. So let's look at some statements here. So a statement in mathematics is a sentence that is known to be true or to be false. Okay, it's just a statement. So it's different from an opinion, right? So write a statement about your math teacher that you know to be true. So I'm Ms. McKay. Maybe you say, Ms. McKay wears glasses. Write a statement about your math teacher that you know to be false. Well, you might say, Ms. McKay is young. Because I've told you, and you know that I'm not young. Well, I'm young at heart. In any case, is the following sentence about your math teacher considered to be a statement? So remember, a statement is known to be true or false. My math teacher is the best teacher in the whole wide world. Well, hopefully it is true, but it is really, that statement is really an opinion. So it's not a mathematical statement. You might think your math teacher is the best teacher in the whole wide world. Someone else might not, right? It's an opinion. So it's not proven in fact, where a statement is. Okay, so a mathematical statement. So part B, use the word not. So the word not is used to form the negation of a statement. So write the negation of the statement in question 1. So that would be Ms. McKay does not wear glasses. Now, truthfully, the odd time I wear contacts, but I guess I should say corrective lenses. If I don't wear any of them, I can't really see well. Write the negation of the statement in question 2. So in this case, Ms. McKay still use that word not. Even though the opposite of young is old, there's also some gray area in that one. Ms. McKay is not young. Okay, so just always use the word not and in order to negate something. So the word not can also be indicated using these mathematical symbols. So that's the less than or equal to sign, so a slash through it means not less than or equal to. Okay, so that can be used mathematically. So indicate the following solutions on a number line. So x not equal to 3, so this is all the real numbers. So we want to show every number on the number line in the real number system that is not equal to 3. So we would do an open circle at 3 and basically an arrow going both directions from there. Okay, and that arrow represents every number, except that open circle at 3 means it doesn't include 3. This says x cannot be greater than negative 2. So if this is negative 2 here, okay, it cannot be greater than. That means it can be less than. Okay, and it can be equal to. Okay, so cannot be greater than. That means it could be equal to. So we're going to fill in that circle. So this would be the same as x less than or equal to negative 2. So these are the same. This is just using that slash, which means not. Here, x is not less than or equal to 5. So it's not on the left here, less than or equal to. It's not even equal to. So it's going to have an open circle and then to the right. So this is the same as x greater than 5. Those are the same. Okay. So, compound statements using the word and. So two statements can be combined to make a compound statement using the word and we'll learn the mathematical notation for that as well. So state whether each statement is true or false. Halloween is on October 31st. Sure is. New Year's Day is on January 1st. Sure is. Canada Day is on July 4th. No. July 4th is actually in the United States, Independence Day. Canada Day is July 1st. Halloween is on October 31st and New Year's Day is on January 1st. Yep. Canada Day is on July 4th and New Year's Day is on January 1st. That's false. Even though this is true, this is false. And with the word and, you have to have everything has to be true. Okay? So, cannot say true to that. So a statement using the word and is true only if both parts of the statement are true. Okay? Everything has to be true in order to say the whole thing is true. Write a compound statement about your principal. Well, really it's changed to math teacher, I think, for you guys. It uses the word and that is true. Okay, so that goes back to our first thing that we did. So, Ms. McKay wears glasses. And, okay, Ms. McKay wears glasses, and that is true, and is not young. Okay. Write a compound statement about your, again, teacher that uses the word and, that is false. So that means both could be false or one of them. Okay. So I could keep the first one. Because that's true. But this one is not true. Okay, so that whole statement would be false. All right. Next one, factors of 24. All possible factors of 24. So 1 and 24, 2, so 2, 3, 4, 6, 12, and 24. Oops, I forgot 8, didn't I? 8, yeah. 1 and 24, 2 and 12, 3 and 8, 4 and 6, yeah. Factors of 30, so 1 and 30, this way I don't forget them, 2 and 15, 3 and 10, and 5 and 6. Okay? So the numbers that are a factor of 24 and a factor of 30, so 1, so what's common to both? 1, 2, 3, not 4, not 5, 6, not 8, not 10, not 12, not 15, not 30. So 1, 2, 3, 6. A Venn diagram. So you may have seen Venn diagrams before. It can be used to represent the above sets of numbers. Let A represent all the factors of 24, B all the factors of 30. Enter the elements into these. So A, we would just show them. So 1, 2, 3, 4, 6, 8, 12, 24. 1, 2, 3, 5, 6, 10, 15, 30. Since there are elements that are common to both sets, there's an overlap. So if we overlap them, then that's where we put the overlapping values. So 1, 2, 3, and 6. And then in the other part, that's what's not included. Okay, so what's not included, 1, 2, 3, 4, 8, 12, and 24. 1, 2, 3, 5, 10, 15, and 30. Okay, so I kind of did that. What numbers are in the overlap? 1, 2, 3, and 6. Does not overlap 4, 8, 12, 24. B, 5, 10, 15, and 30. Okay, the overlap means they're in common. And there it is again. I did it as I go. So this here means intersection. Okay, so I think about it as the two ends of that are touching A and B. So whatever values are in both A and B are in the intersection, and that really, the word for that is and. They have to be in both. Okay. So now compound statements on a number line. the location of the numbers described by each of the following. So n less than 3 and n greater than or equal to negative 3. So I just plot, oops, not 4, 3. And n has to be less than 3. So open circle, everything less. N has to be greater than or equal to negative 3. And it has to satisfy both. So that would be in the overlap. So that's why I use pencil. And I erase that part. And I just join these up here. Open circle, close circle. Or you can do it right on the number line. So whatever n value you choose has to satisfy both of these. Another way of showing this would be n in the middle, less than 3, so put them in order. Smallest number on the left, largest on the right. Okay, so now 0 and 2, n has to be less than 2 and less than 0. So where do they overlap? Here. So actually, keep that 2, but I don't even need to graph any of that. This represents the numbers that satisfy. Okay, open circle there. Okay, so this wins out, basically. And then negative 2 and 1. So n has to be less than negative 2 and greater than or equal to 1. Well, it can't. They don't overlap. So this, there is no solutions to this. Okay, because it says and. Now the word or, that's a little bit different. So two statements can be combined to make a compound statement using the word or. State whether each statement is true or false. Canada Day is on July 1st. Yes, that's true. On July 4th? No, we already said. Halloween is on October 31st? True. It's on November 30th? No, it's false. It's only one Halloween. Canada Day is on July 1st, or Halloween is on October 31st. That's true. Both of them are true. Canada Day is on July 1st, or Canada Day is on July 4th. Well, think about it. It's on the 1st or 4th? Yeah, it is. It's on the 1st. So that statement, because of the or, is still true. Canada Day on July 4th or Halloween on November 30th, neither of them are true. So now that's false. So this was false, so the whole thing is. This was true, this was false. So it is still a true statement because of or. This was true, so of course the whole thing is true. Okay, so a little bit different now that we're using the word or. So a statement using the word or is true if either or both of the statements are true. So either one or both. Statement using the word or is false only if both component statements are false. Okay. All right, recall the factors of 24 and 30 that we did before. There's the Venn diagram. The numbers that are a factor of 24 or a factor of 30 is every single number in that diagram. So 1, 2, 3, 4, 5, 6, 8, 10, 12, 15, 24, 30. Which part of the diagram represents the factor of 24 or 30? So or means everything. Both circles. Entire diagram. Right? So, the union of sets is denoted by this sort of what looks like a U. Okay? And so, because it looks like a U, it kind of makes sense that it's the union. So, that really represents the word or. So it's in one set, or the other set, or both sets. So on the number line, indicate the location of the numbers described by each of the following. So negative 2 and 1. So less than negative 2, or greater than or equal to 1. And it says or. So we're good if we, for example, chose the number 2. 2 is not less than -1, but it is greater than or equal to 1. So it does satisfy part of this because of the word or. So you would show it like that, 2 separate arrows. 3, 5. N less than 3, n less than 5. Okay, so in this case, it's really n less than 5 that wins out. It's this whole thing here. Okay, so you don't even need to leave an open circle there. So I'd actually erase that. It might get confusing if you put an open circle. All right, it's everything less than 5. -2 and 1. So greater than -2, less than or equal to 1. That's everything in a set of real numbers. So I'm going to fix this up and just draw the entire thing. Okay, you can put -2 and 1 there, but it's all real numbers. Okay. So, interpreting a Venn diagram. So, getting a little bit more specific with actually the number of items in a set as opposed to the actual elements, like those factors that we did. So, the Venn diagram below displays the results of a survey of several families regarding technology in their home. Okay, this is a little bit outdated. Probably there's no VCRs. We may have updated yours to be at least a DVD player, but bear with us. So C represents the number of families with a computer, V, VCR, F, fax machine. And again, a lot of people don't have fax machines either unless they're business people, because you can have a scan, right? In any case, looking at that, so there's different parts to this. So notice how they're in a rectangle or a square, almost looks like a square. That means this is the whole survey, okay? So this number out here, what do you think that represents? That would represent the families that were surveyed that had none of these, okay? This 1 represents the families that have a fax machine, but nothing else. As opposed to this 4, which represents families that have a fax machine and a computer. This 5 represents families that have all 3. Okay, so where it's located tells you different things. So how many families have a computer at home? Well, that would be everyone in this circle. So that would be 7 plus 4 plus 5 plus 62, which is 78. Then, how many families have all 3 machines in their homes? As I said, that's the inside number. Okay, so that's the 5, where they all overlap. How many families have a computer and a VCR? So that would be here. Now, be careful on this, a computer and VCR. You might think, oh, I'm not going to count the 5 here. Well, yeah, these 5 people have a computer and VCR. They also have a fax machine, but they do have both. So it's everything in the overlap of those 2 circles. So it's 62 plus 5, which is 67. Okay, and then how many families have none of the 3 machines? That's what I talked about, that 3 on the outside. And how many families do not have a fax machine? Okay, so here's your F, so it's everyone that's not in there. Okay, so that would be 3 plus 7 plus 62 plus 18. So that's 70, 80, that's 90. How many families were surveyed? Well, that would be the sum of everything. So we said the number that don't have a fax machine was 90. So then add the fax machine. That's another 10. So that would be 100. And then what fraction of the families have a computer or a fax machine? So computer or fax is everything in these circles here, right? So a computer, we said, was 78, plus 1 is 79 out of 100. All All right. So that you were given the information on a Venn diagram. Now we're going to actually set up our own Venn diagram. So it says each member of a sports club plays at least once of soccer, rugby, or tennis. The following information is given. Draw a Venn diagram to illustrate. Okay, so I'm going to do a big kind of like to expand that. Can I do that? Okay, we're going to just sec here. I'm going to do, there we go. There's a rectangle. I'm going to do 3 circles. And then a cone. All looks like the Olympic rings, except there's only 3 of them. Okay, so it says draw a Venn diagram to illustrate the members of the sports club and the sports in which they play. So you want to label these. So we've got soccer, so I'm just going to call that S, rugby, tennis, doesn't matter where they're located. The biggest thing is you want to start either from the inside, the overlap, and work out. If you know the number of people that are not in any of the sets, you can also start there too. In this case, it says we know the number that play tennis, but that's for the whole circle, so we don't know what the overlaps are. So we want to look for anything that says and or all 3. So it says 4 play all 3 sports. So 4 is going to go in there. Okay. Then we want to look for the words and. So up here, soccer and rugby. So 6 play soccer and rugby. So that means in this overlap here, you have to get 6. So we've already got 4 there, so that has to be a 2. So don't forget, this already counts for people that play soccer and rugby. Okay, they happen to play tennis too, but there's 4 of the 6. And then tennis and soccer is 7. So 7 minus 4 is 3. And tennis and rugby is 11. So 11 minus 4 is 7. So now we've worked our way out of the overlaps from the inside out. Okay, so now we mark off what we've done. We've done these. All right. Then we've got some or statements. We've got tennis in total. We could actually do the tennis in total, 43, because we've got all 3 of the parts. We're just missing this fourth part here. So 43 minus, that's 14, is 39, 29. So 29 play tennis only. Then, so we've got that part. We've got rugby or tennis is 84. So take a look. We have to have only one part missing in order to use the information. So rugby or tennis is everything in these 2 circles. And so the only part missing is this. So we can figure that out. So if you think about it, tennis only, or the whole tennis is 43. So that's this. Plus 2 is 45. And tennis or rugby, so this would be 84 minus 45. So that'd be 79, that would be 39. Okay. And then soccer or rugby, now we only have one part missing. And so that would be, so 39 plus 7 is 46, 52, 55. So that would be 68 minus 55 is 13. Okay? And it doesn't say that, well, obviously if they're a member of the sports club, you assume they're going to play some sports. So there's nothing outside here. So then it says, I think it asks you, how many members does the club have? So you'd add them all together. Faster way would be, you already know, for example, soccer or rugby is 68. So then we just add 29. So 68 plus 29 is 97. So 97 people in the club. Okay, and that's it.